Hi friends, welcome to this YouTube channel. This is lecture number 5 and today we are going to study power diodes. So without wasting time, let's start the video. As you all know that a signal diode is a PN junction device. Now what is power diode? Power diode is also a PN junction device, but it has some constructional changes. Signal diodes are rated for few volts and milliamperes, while power diodes are rated for kilovolts and kiloampere. Now I tell you the applications of power diode. Power diodes are used in freewheeling diodes and they are also used in rectifier circuits. They are used for recovery of trapped energy. Although basics of diodes are covered in subject electronics, but to revise your concepts, I will tell you all these basics again. Now we start with PN junction. So what is PN junction? A PN junction is formed when p-type semiconductor physically contact n-type semiconductor. P region has high concentration of holes and low concentration of electrons, while N region has high concentration of electrons and low concentration of holes. Now one important thing I want to tell you is that wherever you see this P positive sign, then it indicates highly doped P region, and wherever you see this N negative sign, then it indicates lightly doped N region. Now we will discuss how the depletion layer is formed. This is important. When P region and N region make contacts, then electrons from N region diffuse into P region. And when they do so, they leave a positive charge behind. Here we see that electrons from N region diffuses into P region and they leave this positive charge behind. Similarly, holes from P region diffuse into N region and they leave a negative charge behind. Due to this diffusion, N region has positive charge and P region has negative charge near the junction. This is junction. These charges across the junction produce electric field. This field stops further diffusion of charges. So each side of junction remain with these immobile ions. This region extends into both P and N region. So this is the width of depletion region, and this width is extended in both P and N region. And this whole region is called depletion region, or it is also known as space charge region. Potential difference across this depletion region is called barrier potential Vt. Okay, so this barrier potential Vt is equals to 0.7 volt for silicon and 0.3 volt for germanium. As you all know that a forward bias diode means when the positive potential is applied to anode and negative potential is applied to cathode, then the diode acts as forward biased. When the negative potential is applied to anode and positive potential is applied to cathode, then the diode is reverse biased. Here important point you must remember is that forward bias is inversely proportional to the width of depletion region. It means when forward bias increases, then width of depletion region decreases. Also, reverse bias is directly proportional to the width of depletion region. It means when reverse bias increases, then width of depletion region increases. Now take another very important point, and it will be utilized in SCR and diode working, and this is really very important point, so you must remember this point. If the region is lightly doped, then width of depletion region extend more in it, okay, and it has large breakdown voltage. And if the region is heavily doped, then width of depletion region extends less into it. and it has a small breakdown voltage. So this is very important concept and you must remember this. Now we see the construction of power diode. See the diagram of power diode. It has lightly doped N positive and negative region and a heavily doped N positive region near the cathode. So, as this N negative region is lightly doped, so it has depletion region extend more into it. Okay, this is because of this point. That's why this lightly doped region has high reverse blocking capability, or we can say that it has high breakdown voltage. The thickness of this region, this is responsible for high breakdown voltage. Because of this N negative layer, power diodes are called PIN diode because this N negative layer is nearly intrinsic. That's why power diodes are also called PIN diode, and this N negative region is responsible for high breakdown voltage of power diodes. Now we will see the VI characteristic of diode during forward bias. As forward voltage increases, forward anode current start flowing, but this current is very small. Up to threshold voltage Vt, that is nearly equals to 1 volt. This is Vt and it is nearly equals to 1 volt. Or it is also called cut-in voltage. This forward anode current is very small. And beyond the threshold voltage Vt, this anode current rises rapidly and diode start conducting. When diode is reverse bias, then a very small amount of current that is equal to reverse leakage current flows. When reverse voltage go beyond the breakdown voltage VBR, then what happens? Then this reverse current increases abruptly and this high reverse current may destroy the diode. So this situation must be avoided. In this way, we can plot this forward and reverse characteristic. For ideal diode, cut-in voltage is equals to 0 and breakdown voltage VBR is infinity. That's why we get this characteristic of ideal diode. So, another important point that I want to tell you is that manufacturers generally indicate inverse voltage, that is peak inverse voltage, and it is equals to VBR. Why they indicate this? Because we need to avoid this situation. That's why they indicate peak inverse voltage. Now these are the waveforms for diode recovery characteristic. This portion of chapter is actually important. When diode is in forward bias, then it takes time T off to turn on. During turn on, anode current rises linearly from 0 to IF. Once the diode is turned on, then the current through diode is IF and voltage that is equals to VF. Now when the diode is reverse bias, that is at this point, the anode current starts decreasing linearly. After forward anode current decays to 0, the diode continues to conduct in reverse direction. This is because of pressure of stored charges in depletion region and semiconductor layer. Now to regain the blocking capability, the reverse current must be 0. Or we can say that at this point when this reverse current is 0, diode regain its blocking capability. So how we can calculate these stored charges? The answer is charge is equals to current into time. Or we can say that Q is equals to IT. So area under this IT curve gives the stored charges. So what will be my stored charges? That is equals to this area. So this area gives the charges stored in depletion region and semiconductor layer. Now we know about these time periods. This TRR is the time instant when anode current becomes 0 to the time when anode current achieves the value 0.25 of IRM. What is this IRM? This IRM is the maximum value of reverse recovery current. So this time period is TRR. Okay, this time decides the switching frequency of any circuit. Now TA, this is TA, it is formed when anode current becomes 0 to the point when anode current reaches the maximum value in reverse direction, that is equals to IRM. During this time, stored charges in depletion region are removed. And next time is TB. It is the time between IRM, that is maximum reverse current reached, to the 0.25 IRM. During this time, charges from semiconductor layer are removed. Okay. Now what is QR? It is the total stored charges and it is represented by this shaded area. So the conclusion is, during time TRR, what we have to do, we have to remove all these charges stored, that is shown by this shaded area. In short, we can say that total stored charges QR, that is sum of stored charges in depletion region and semiconductor layer, must be removed in time TRR, and TRR is equals to TA plus TB, and in TA the charges from depletion region are removed. In time TB, charges from semiconductor layer are removed. Okay. Now please note this important point, that is softness factor. Softness factor is equals to TB by TA. If softness factor S is equals to 1, then diode is called soft recovery diode. If S is less than 1, then diode is snappy recovery or fast recovery diode. When S is less than 1, so it is snappy recovery diode. In case of fast recovery diode, this TA is greater than TB. That's why we are getting S is less than 1. So we can say that total time TRR, that is equals to TA plus TB, is nearly equals to TA. Now TRR is equals to TA plus TB. And di by dt, we know that it is equals to change in current upon change in time. And we know that when current changes from 0 to IRM, then it happens during time TA. So we can say that di by dt is equals to IRM by TA. From that, we can say that IRM is equals to TA di by dt. QR is the stored charges, and that is equals to area under IT curve, that was shaded area. Now see, this shaded area can be approximated as a triangle whose base is TRR and height is IRM. So to calculate the charges, we have to calculate the area. So area of triangle will be equals to half base into altitude. That's why we get 1 by 2 IRM into TRR. You must know that for fast recovery diode, as I told you, this TB is nearly equals to 0 because it is very small, and TA is much greater than TB. That's why we are getting S is less than 1. So for snappy recovery or fast recovery, we can write TB nearly equals to 0, and putting TB is nearly equals to 0, we get TRR is equals to TA. Now using these three equations, that is A, B and C, we can write QR is equals to half di by dt TRR square. This formula has been directly asked in ES 2004. Now this is question based on this formula. The reverse recovery time of diode is 3 microseconds. Here TRR is given as 3 into 10 to the power minus 6 seconds. And rate of fall is di by dt is 30 ampere by microsecond. It means di by dt is given. So this is question with direct formula. So here we will put TRR is equals to 3 microsecond and di by dt is equals to 30 ampere per microsecond. Then we will get QR is equals to 135 coulomb. Now classification of diode. Diodes are classified based upon the time TRR. For general purpose diode, TRR is nearly equals to 25 microsecond. They are rated for kiloamperes and kilovolts. They are used in rectifier circuit. Second is fast recovery diode. For them, TRR is nearly equals to 5 microsecond. They are rated for few hundred ampere and 3 kilovolt. They are used in transistor and chopper. Third one is Schottky diode. For them, TRR is nearly equals to nanosecond. Rated for few 300 amperes, 100 volt, and they are used in SMPS, that is switch mode power supply. They are fastest diodes. You must remember all these 3 points. There is no need to remember all this rating. Only you have to remember the time TRR. And you have to remember that Schottky diodes are the fastest diode. This has been asked in ES 2017. Second important point is breakdown voltage is inversely proportional to the doping density of drift region. This concept has already been told to you. Vertically oriented structures support large breakdown voltages or large blocking voltages. So this is another important point. Okay, so this is all about this video. I hope you like the video. Thank you. Jai Shri Ram. If you got the knowledge and concepts from this video, then please like the video and subscribe the channel. You can give your views and ask any questions related to this topic in comment box. Also share this video with your friends because sharing is caring. Don't forget to press the bell icon to get the notification of my upcoming videos. Thank you.